Okay, so this is part two of the second lecture. And in this lecture, we're going to talk about unsupervised learning, reinforcement learning, as well as how we can start to think about, applying these ideas to game development and simulation and that. So this is a continuation of the last lecture and then the part one of lecture two, which I split up into two pieces because, I recorded it all on Monday and it all got destroyed because the microphone was not working. So it's working now. I made sure. Let's get to it. So in the last lecture, we talked about supervised learning, and in supervised learning, just to kind of remind you all, the idea is we get a data set that includes both the data as well as some kind of underlying structure, generally in the form of ground truth, such as labels for images, or in the case, for example, of house prices, we have a bunch of different attributes of a particular house, such as its square footage, its location, how many floors, how many rooms, bedrooms, whatever, and then a bunch of these data points, including the respective, value of the house. So in that context, we have this large data set, and we also know for each data point what the value is, what's the answer, what is the sort of transformation, and so it's very kind of directly possible to take that data, transform it into that resulting value by way of a model that we can then train and get better and better and better at fitting that data. And then when we get a new piece of data, one that we haven't seen inside of our model, we can then plug it into our model and get what we think is a prediction, and hopefully that's going to be somewhat representative and predictive as well. So unsupervised learning kind of flips the script a bit. We're given a lot of data. So imagine that same data set, for example, with a bunch of housing, and it's a bunch of different things like numbers of bedrooms and size and square footage and what have you, but we don't have house pricing at all in this data set. We just have a lot, like millions of houses information. And so what we're trying to do with unsupervised learning is we're trying to operate directly on this unstructured data, because we don't know what this data means. We just know these are a bunch of houses somewhere and the information about them. And we're trying to sort of extract from that data some kind of structure. One class of methods here that we'll talk a lot about are these maximum likelihood methods. And in this context, we're trying to determine a probability distribution function that sort of matches that data. So on the right here is the sort of formal declaration of this like log likelihood model, where we're trying to maximize the logarithmic probability of our p theta, our probability distribution that we've sort of determined that is parameterized by theta. So once again, you see that we have these parameters that then determine our probability distribution function that we then plug our data into. And so often what we do is we don't maximize this. Instead, we minimize it. So we just minimize the negative log likelihood, because many of our frameworks will be better at minimizing than maximizing. But it's the same idea. It's just sort of multiplied by -1. It's the same concept. So this is a kind of a thing that always took me a little bit of time to kind of wrap my head around. And the example that I like to show to demonstrate this is the example in the top right corner here. So imagine these blue dots. These blue dots are data that we've observed. So we see a bunch of numbers around 10 and numbers around 9, and we see a couple of outliers at 7.5 and near 12. And then we try a bunch of these different probability distributions. So in this case, we're trying out the Gaussian distribution, the normal distribution. So first off, we try this green curve, and what we do is we take all of the values and we plug it into that curve being just the Gaussian. So we take the value 7.5 and then extract from that the probability distribution of that value in that curve, which is just sort of the area under the curve. And we can talk a little bit about how to do this with a probability mass function versus a probability density function. But just kind of bear with me that for whatever reason we're able to sort of figure this out. And we try to then maximize the probability. So we see for the green curve, the sum of all the likelihoods of these values is going to be less than the blue curve. In this case, the blue curve represents our data much more accurately, where we can see that, for example, all those numbers around 9 and 10 get a much higher value in the blue curve, right? They're getting numbers around 0.2 versus all that density in from like 9 to 10 is getting relatively low numbers in the green curve, less than 0.2. So you can just see kind of visually that we're trying to maximize the probability. And if we can find a model, we can find a distribution or a very complicated function that models our data very accurately, then, well, what can we do with that? Why is that interesting? Well, first, now we know the underlying structure of our data. But more interesting than that, oh, great, this thing again. What we can do is we can start to kind of, figure out what our data is doing. And that's very valuable because there's a lot of utilization, such as saying, oh, there's a cluster of these data points. Maybe we can kind of classify these into a certain kind of class. There's an alternative where if we know that distribution, and we want to generate new data that doesn't exist, then we can just sample that probability distribution. And so we'll talk about kind of both of those in this lecture. So one kind of classic utilization of unsupervised learning is what's called clustering. As we just mentioned, if I have a lot of data that's not really representative of anything, as is shown in this plot with blue points, if I can sort of find a way to cluster the data, to kind of find relationships between the data that split it up into a certain number of clusters or classes, right? I don't know what those classes are, but perhaps if I do that, then I can start to kind of understand what my data is doing and what kind of potential classes are there. So this is actually what a lot of recommendation systems do, right? Where, say, you listen to a particular song and you're now in a cluster, and you can then kind of map, oh, if you like this song, you might like these other songs as well. Another thing to do, but by way of clustering similar songs to each other, by the way, right? So if you like this song and a bunch of people like this song, and then you don't like this song, but hey, it's close to where you are, then you might like that one too. So that's a very common way to build a recommendation system. Also, this is the way that Google News works, where Google News gets a bunch of millions of articles a day and has to sort of figure out of that what news articles are relevant. And what it's doing is it's clustering different news articles on similar subjects to each other. And it doesn't know what those subjects are, right? It's not like the algorithm saying, oh, this is a lot of news about the U.S. And knowing that the U.S. is a thing. It just knows, oh, all these articles are talking about the same similar thing, and they seem to be ranked high. There's more of them than this other next cluster, and that's how it kind of ranks the most relevant news articles in a particular day, and then ensures that you can have a bunch of different news sources for the same event or the same kind of thing. And the way that it kind of represents the distance and the similarity between those articles is a more complicated thing. But just kind of at a high level, if it has some similarity index between data, right, some kind of this dimensionality between them, then it can sort of cluster them together into these groupings, which can then be presented to users without even knowing what the stories are and what classes and what that relationship even is. So this is actually an example. Clustering is a kind of example of just general dimensionality reduction. And the dimensionality reduction is literally what it is. If you're familiar with SVD or SVD being the underpinning for PCA or principal component analysis, which we may talk about in this course as well. But imagine you have really high dimensional data. For example, images. So in this case, on the right, you have this image of this process called TSNE, which is a popular dimensionality reduction technique. And what this is showing is it's actually against the MNIST data set. The MNIST data set is just a lot of these images, these 32 by 32 black and white images of handwritten digits. And so you can already hear the number of dimensions in these very small images that are black and white are 32 times 32. It's quite a large number. And so I want to be able to map 32 times 32 dimensions down to 2 dimensions. I want this XY sort of representation of the data. And so TSNE allows me to reduce that dimensionality down. And you can see these groupings. And so the coloring was added after the fact to represent, the different class. So you can see up here, I guess I don't have a mouse right now, but that's fine. Up in that purple or cluster is all the zeros the blue is 1, the red is represented by 8. And you can see how the t-SNE algorithm has sort of separated them to sort of occupy different areas of the XY sort of space. Now, what's important to note here is the t-SNE doesn't give you these classes, right? We actually colored these points based on the original classification. So this is actually kind of it's a semi-supervised process because we've reduced the dimensionality in an unsupervised fashion, but then we've colored these points using a supervised fashion because we know the 1 is a 1, we know the 7 is a 7. And you can imagine if we didn't have that classification, this would be a very difficult problem because look at the 8s, right, represented by red, so that one bundle is particularly well encapsulated, but there's also this segment in the 5 and sort of in the top left portion of the green cluster where there's a lot of 8s there. So just looking at this, you would see a number of 8s and classify them potentially as 5 accidentally. So this is kind of an example of what unsupervised learning can also often be used for in kind of conjunction with supervised learning. As I mentioned in the last lecture, a lot of these approaches and these paradigms are not separable, they're not mutually exclusive. You often use them together. So for example, say I have an algorithm that is a very expensive algorithm. It uses a lot of parameters and is directly proportional in computational cost to the input of the algorithm. Say I want to be doing image classification on an image, and if I do it on a 64 by 64 image, it's not tractable given the computation that I have access to, say I'm on a mobile device or something. But in 32 it is. So one thing I could do is I could downscale it. Another approach would be to reduce the dimensionality using t-SNE or principal component analysis or other things like that, where what I'm really doing is I'm removing basically components of the data or dimensions of the data that are not relevant to the underlying structure, right? Like one example in this particular case is I can look at the data right now in the MNIST data set, and we have a bunch of these values, these handwritten digits, or you can look at these images and say, actually, the borders tend to be pretty empty, right? And so t-SNE or principal component analysis will come along and say, hey, these particular dimensions are always 0 and never actually do anything for you. You can just throw them away. And per this data set, you can actually, on average, remove these components of your data and still have the same kind of performance. By the way, principal component analysis specifically will take your data and project it into a smaller sort of space. So it's a very, if you're interested in that, we'll discuss it. And please let me know again in Discord or an email or however, if you're interested in particular in these kinds of techniques, which are very, very useful, by the way, for games, because I just mentioned the magic word, which is projection, right? So if you have big data and you want to sort of project it into a smaller space, this is something that's very applicable for, in particular, AI decision making for like behavior trees and that kind of thing, right? Where you have 20,000 different parameters and variables in your game state, and you want to only make a decision on the important ones. PCA is your friend. Cool. Apparently, I can't. Cool. Okay. I'm very good at technology. So, the very exciting thing, in particular for simulation in games, is generation of new data if we know the underlying structure of a particular set of data. If we do know this underlying probability density function of our data to an arbitrarily accurate degree, then we should be able to sample that probability as well. And if we can do that, then we can generate new data that we have not seen that is still hopefully looks like, feels like the data that we put into it. And so this is, again, a unsupervised technique. However, done in a semi-supervised or sort of meta-supervised way. Say I give you 10,000 images of a dog, right, and you can learn the underlying probability distribution of what dogs look like, and now you can generate new images of dogs that were not part of that original data set. Now, why is that unsupervised? Well, the data has nothing about the dogs and what dogs look like. You just have to figure out from that and extract from it that underlying representation. However, you do know they're all dogs, right? So we've kind of skipped this step of sort of figuring out, I'm not just giving you a bunch of images and you are pulling out from them the images of dogs. you are just doing it on these things, sort of knowing that these are all dogs. So you can kind of see, again, this sort of meeting between unsupervised and supervised learning, where often what you'll do is use a supervised technique to get certain amounts of certain data that then you can use into unsupervised learning and then pull it back into a supervised technique. For example, if I can generate new images of dogs and then train a particular classification model on this new probability distribution, maybe I'm going to get a better classifier than just if I'm doing it on the 10,000 images of dogs that I have access to. So there's a lot of research on this subject, and I'm not by no means an expert. But if this is something that's interesting to you all, please let me know. I'm happy to dig into it, as we'll talk about it a lot in this lecture. So there's a number of different approaches to generative models, and they're all kind of based on maximum likelihood models, as we've been talking about up until now. We are trying to maximize this underlying probability distribution function to represent the data that you're seeing in this unstructured data set. They split up into two main categories, one of which is explicit density, and the other one is implicit density. And by explicit versus implicit, in explicit we are directly trying to determine that probability distribution function, and implicit we're not. We're doing it by way of some kind of latent representation or some kind of implicit representation that doesn't actually give us that actual function directly. And explicit kind of further diversifies into two different kinds of density, two different kinds of approaches, one of which is a tractable density approach, where we're literally calculating the density function directly and applying it, generally in an autoregressive fashion, or we are approximating it, which is the case in variational autoencoders, and we'll talk about that in this lecture. So let's talk first about approximate explicit density functions. These are a little bit mathy, and I'll talk a little bit at length at this one because this is a very interesting sort of idea, and one I think that if you're all interested in, I'd be very happy to kind of dig into more, and this is something I'm personally investigating myself. So what variational autoencoders are doing, or these approximate explicit density these models that are trying to approximate the density function explicitly, often, in the case of variational autoencoders, are utilizing the variational information maximization idea, where we might not be able to, directly learn this probability distribution function, but if we can sort of define this idea of mutual information between this distribution function that we're kind of after and one that we've sort of approximated, we can, by way of variational information maximization, prove that our approximated density function, the mutual information between it and the actual distribution function, is a lower bound to the actual information. I'm slaughtering this. On Monday I explained this so much better. I apologize, but I'll add some errata here as well to the thing. But what this really kind of distills down to is that we're trying to minimize this KL divergence. And the KL divergence is sort of one set of divergences in the general F divergence, which is sort of representing how similar two distributions are to each other. And what we're doing is we're trying to minimize the divergence between this one distribution function, which is conditioned on our input. So we have input value, input image, for example, like in the case of the bottom right, this 3, which we plug into this distribution function, which gives us the likelihood of a particular prior distribution that we're extracting z from, given conditioned on that input data, and that gives us this z representation, which is in of itself drawn or represented by a probability distribution function of its own, usually a Gaussian or a uniform or something like that. And then we have an additional probability distribution function that sort of takes our z representation and then is conditioned on, is basically gives us the probability of the input of the original x conditioned on z. So these are two distribution functions. They're quite complicated. And we don't really know them. There's no way to kind of tractably, calculate these things. So we approximate them by way of a function approximator that we've been chatting about in the last lecture. And this is, so in other words, we're using both for Q and for P a neural network that then sort of tries to approximate these probability distribution functions given a particular prior in PZ. And what we can show with variational autoencoders is if we have these two, if we minimize the KL divergence, this acts as a way of maximizing the lower bound on the mutual information between the probability, the transformation of our data to the actual underlying ground truth of the probability distribution given our unstructured data. So I'm happy to do a full lecture on this particular subject because this is something that I myself am trying to get better at and more understanding of. This is a very kind of like hand-wavy, very informal introduction to VAEs. But it's a very powerful idea because one of the things that we can do now is, say we have now taken a lot of data. What we're really doing is we're using this autoencoder. All an autoencoder is doing, by the way, is it takes input data, tries to convert it using some kind of function approximator to a latent space, and then takes that latent space and then outputs it again by way of a neural network to the original output data. And the difference between a VAE, a variational autoencoder, and an autoencoder is that autoencoder is just doing a kind of Euclidean distance, so the input and the output, you want them to match. And with a variational autoencoder, it's shown that if you try to minimize this KL divergence between P and Q, you also are determining these. You're more directly trying to solve for the probability distribution function that takes you from the X space to this latent Z space to then again back to the X space. And that is the really valuable thing, because now, say I've trained these two networks that are able to convert to Z and then back out again. Now Z is represented by some kind of uniform, some kind of distribution, be it normal or Gaussian or what have you. So now all I have to do is sample that prior distribution of Z, right? So let's say it's a normal, I'm just kind of randomly choosing data from wherever I want, and I just plug it into my network, to my function approximator, Px of Z. And so that's very easy to sample, and in theory I will get very, very different kinds of data by doing so. It's going to be random data that I haven't seen yet that is still correct, and again the P and Q have been the mutual information is going to try to match, and what that means is they're very similar in theory, and in that sense the output data from our Z is going to match our input domain distribution very, very well. Now the problem with this approach, as you can kind of already see in this image, is the result is kind of blurry. Because we are maximizing this lower bound on mutual information, while we're getting kind of close, we're never quite going to match exactly the exact function, the exact identity function of that information. And that means that we're always going to kind of be a little bit blurry. And we can always improve and get better and better and better, but this is still very much a kind of active area of research. And if you're really interested in this, we'll talk about InfoGAN in this course as well, where InfoGAN utilizes the sort of implicit approach, but takes advantage of these sort of F divergences. And while it doesn't use the KL divergence, it does use not the Shannon-Jensen, but it uses a different one. I forget, but it uses a distribution divergence and minimizes that as well per the GAN loss function, as we'll talk about very soon in this lecture, and allows you to sort of bring in this sort of variational information maximization concept into an implicit model as well. So it can be a very kind of useful idea that can then be applied to more state-of-the-art technique. This is not state-of-the-art. This is state-of-the-art, but it's the results are not as state-of-the-art as, say, GANs, which are currently kind of like leading the way, although there are many other approaches. Cool. So moving on to tractable explicit density. So in this case, we're trying to directly come to this probability distribution function conditioned on our input data. And this is largely based on Bayesian inference, or also what's called Bayesian networks. And the way we do this is we kind of recurrently apply this model over and over and over again. So this has been shown to work really well for example, sounds, like sound waves, and even for images. We'll talk more about these, but these are also known as autoregressive models, where every single output is conditioned on the probability of the previous values. And that probability function is, again, a function approximated against what we believe is our density. So we're explicitly trying to approximate that distribution function in a tractable way. And this is usually done by way of a recurrent kind of model, or also what's known as an autoregressive model as well. And so there's a lot of sort of research going on in here, and I do recommend you all check it out. We'll talk more about these in the course when we get to the unsupervised learning portion. Now, to kind of one of the more exciting aspects of generative modeling and unsupervised learning is generative adversarial networks. These use a very different kind of approach, where instead of trying to directly derive this probability distribution function, we're doing so in sort of this implicit way. And the way that this works is sort of this using this kind of game that these two neural networks play with each other. And the idea is this minimax game, where one network is trying to generate images or generate data that it's then trying to fool the other networks. So you have this generator network, which is trying to generate data, and you have this discriminator network, which is trying to discriminate between whether it being a real or false piece of data. And in a kind of flip-flop fashion, you're basically training one to discriminate against whether it's real or not, and the other network is basically its loss is determined and its objective is determined by how often it's able to trick, how often it's able to convince the discriminator that fake data is correct. And the long-term sort of result is hopefully the discriminator, over a long enough period of time, will have a 50% chance of correctly detecting whether or not the data is correct, is fake or not fake. You can see this codified in the algorithm here in the bottom right, where we will update the discriminator by way that the loss is related to how often it correctly identifies true data. So xi in this case is correct data. So this is, say, like a bunch of faces, and then it also is penalized for when it incorrectly thinks fake data, which g of z, so z is our latent space as we saw before, how often g of z it thinks is correct. So you can kind of see it's trying to maximize this, in this case it's trying to maximize the likelihood of being correct. And then once we do that for every case steps, but then for once we do, we also kind of then intermittently will train our generator, and our generator will be trained kind of equivalently on how often the discriminator is incorrect, and we're going to apply that, and so it's going to maximize one to minimize the other, and it's a pretty eloquent sort of solution. And so, yeah, as such, the data that we're using to train this thing never has to be labeled, and what you're doing really is you're taking this latent space, this z latent space, and then pushing it into this sort of arbitrary generator network, which is trying to implicitly approximate whatever it is this probability distribution function is of this underlying data. And this technique is very, very effective. And so these are a couple of examples of CycleGAN. CycleGAN is actually a conditional network which is able to sort of take and apply a certain set of conditions and apply the same thing with deep style transfer. StyleGAN is one of the more sort of state-of-the-art techniques that sort of like implicitly represents the data and in a way that then extracts styles out of that, so you can kind of manipulate individual styles in a very, very interesting way. And you can see just how photorealistic these images are. So in the top left corner, you've got CycleGAN converting a horse into a zebra. In the bottom left, deep style transfer, which I'm sure you've seen in many apps, where you can basically take a a image and then apply to it a Monet kind of style, and then it'll apply that in a way where what it's doing is it's trying to convince a discriminator that this image has been generated by the, it's more similar to the style image, so that it's part of that set, part of that distribution, but it's based on the original, and you can kind of slide the different kind of contribution between the two. And then StyleGAN, as you can see, these are images of people that are largely photorealistic, and if I didn't tell you, you would say, oh, these are real people, but they are not. These are completely generated images, which is somewhat scary because they look real. So that's kind of the end of that. The whole world of generative and unsupervised learning models is quite large and growing. There's also things like GLOW, which is very interesting, and these flow models, which are very similar to autoregressive models, as we talked about, and we'll go deeper into that when we actually do this in the course. Another application of unsupervised learning in NLP and natural language processing is this concept of word embeddings, and I think this is a really interesting one. And important to note that what it's doing is you're giving it a corpus of text, and from that it's trying to extract the relationships between different kinds of words. These embeddings, there's a couple of them that are relatively popular, like word to vec and glove, and the goal is to, given a corpus of text, now you have this matrix. So say your dictionary is the number of words that you want to represent is 10,000. So you would have then a matrix of 10,000 by 10,000, and at each, the diagonal will be 1 because every word represents itself. And for every word, you would have some kind of value that sort of gives you a relationship between that value and another value. And this is what the goal is to kind of create these embeddings that mean something in Euclidean space relative to one another. So for example, if I take the embedding for the word king and subtract from it the embedding of the word man, now I have this embedding that represents the difference, the Euclidean distance between king and man. And what we want is we want a system, an embedding, such that when I then take the embedding for the word woman and I add to it that embedding of the difference between king and man, I then get a embedding that is relatively close, if not exactly the same, as the embedding for queen. And what you can do with word to vec and glove is exactly that, where you have these sort of relationships that result in, when you do this, you kind of get these very interesting abilities to then manipulate words in this more semantic type of approach, where I can add words to other words or subtract and get these relationships and then manipulate them in interesting ways. One note, everybody's heard about machine learning bias, and this is actually one of the places where it's most prevalent, because you have situations here where you say you do the same idea, where you take the embedding for engineer and you subtract from it the embedding for man, and you take that value, you add it to woman, and then all of a sudden you don't get engineer, you get housekeeper or some stupid thing like that. And so you have to be really aware that of bias in your data sets. Because what's going to happen is your data may have a lot of examples of men being engineers and women being housekeepers for whatever reason. And so this is actually a really active field of research in machine learning in general, is trying to avoid bias in data. This is, I think, the easiest example to explain of bias in machine learning. But there's a lot of other places of this too, right? Even in images, for example, imagine all the images of cars that you've seen in your life, how many of them have been from under the car or on top of the car? So even large data sets such as cars and planes and so on can be very biased, and as a result the machine learning algorithms will learn features and will learn aspects of your data that you may not be intentionally trying to get it to learn. So it might work well in your training and in your test, even in your validation, but when you take it out into the world, all of a sudden you see these things happening that you really did not intend. And that's kind of the definition of bias in machine learning, and something that you should all be very, very aware of. And if it's something that you're interested in working on, please let me know, and maybe we can do something there. So with that, let me go into reinforcement learning a little bit. And this is a very different kind of paradigm than unsupervised and supervised learning, where in unsupervised, again, we have structured data. In supervised, we have structured data. In unsupervised, we have unstructured data. And in reinforcement learning, what we're trying to do is we're trying to help an agent make a decision given an environment. And sort of formally defined, the reinforcement learning problem is an agent provides an action to its environment, and in return, given a state, so it's in a state initially, and then the environment then returns to it a reward and a new state. And the goal of the reinforcement learning problem is to maximize that reward over a given amount of time, and given a particular policy. So there's some kind of policy that is used to determine what the next action might be, and the optimal policy is the one where we've maximized the expected return of reward over a particular time frame, be it a infinite horizon or a finite horizon sort of time frame. So seems like a very easy problem. Actually not, because actions can be complex, states can be even more complex, and rewards are hard to define in many cases. And so, while this problem has been solved and shown in more traditional mathematical ways, there's also ways to do this with deep learning. So you apply supervised or unsupervised techniques to then encode the state of a particular environment. So, for example, in the case of trying to beat all these Atari games, which was shown with a deep reinforcement learning with double Q learning paper, which I recommend you all read, and we'll talk about in the course. The pixels of a particular game were encoded into a particular state, which was represented in some kind of neural network, which was then also used to determine what the best optimal next state was going to be. And this utilizes this concept of the Q value function, which doesn't just encode the potential value of a particular state. We'll talk a lot more at depth on this when we get to this section in the course. And I do recommend this be one of the things that you guys explore, because this is obviously very clearly applicable to games. But the Q function encodes the expected value from a particular time step given the next action you take, and then the future reward from that new state that you arrive at given an action. And so it encodes both the state and the action into one value, which can then be represented as it's a very complicated function, like who knows, right? But if I can encode that and learn it, then from that point on, I can then approximate that function using a deep neural network, and apply that and use that to determine what my next ideal action should be. And this is really notable because this particular approach has reached superhuman capability in pretty much any Atari game, and you can give it a new Atari game and most often it will beat it. Not all Atari games, like Montezuma's Revenge has been traditionally very difficult to beat for whatever reason, a lot of sort of unclear value trajectories and things like that. But it's been shown that this technique can teach an agent how to play a game that can generalize to other games as well. One of the more exciting applications of reinforcement learning in particular is to robotics, and in particular with regards to the applications for simulation and games. Robots exist in a very complex state space, right? Just like a hinge can be in so many different states, let alone a degree of freedom robot. One of the really cool examples of the software problem here was shown by Peter Abil, where he basically showed this video of all these robots like doing the dishes and folding the laundry, and people were like, oh my god, like AI can do this. And then at the end he was like, no, AI can't do this. These are remote controlled robots, but it just kind of proves that the hardware is there, but the software is something that we can't solve. Now the real challenge with robotics, this is a kind of a reinforcement learning problem. You have an environment, and if you can define these, this reward and how the robot should behave, in theory, you should get to a point where you can train a robot to do a bunch of different things. The issue is, how do you get that data, right? That data where you're going to put a robot into every possible scenario and make it do every possible thing. And so in reinforcement learning for robotics, simulation tends to be the sort of way to go. It's kind of the only way to generate the amounts of data that you need to use to then train these robots. And you can do this either in the loop or separately or what have you. But this is a big kind of area of research for synthetic data, which we'll talk about at length in this course. And is also, as you all know, I'm at Unity, and that's sort of what my team deals in, is dealing with how do you generate synthetic data using an engine such as Unity or otherwise. So, these are all really cool things, and I mentioned kind of here and there why this might be interesting for game development and simulation. But why is this really useful? Because in games and simulation, these are domains where we control everything, right? We have the engine, we have these goals, we want to craft things the way we want to. The stuff that I've mentioned so far is by no means an exhaustive list, and what I'm about to kind of go into in potential use cases is also not exhaustive, and I encourage you all to kind of explore your own things that you're interested in doing, because this is the point of the course. The point of this course is to explore this, to kind of go to an arbitrary depth as you all see fit and as interesting to you. And I really encourage you all to sort of challenge me on different ideas and things that I don't bring up. But here's my attempt to kind of point you in certain directions of what you could use machine learning for in games and simulation as a few ideas. So one obvious one, especially as I was talking about the generative AI, the generative modeling stuff, is, well, if we can understand the underlying probability distribution of certain kinds of data, then we can generate new data that doesn't exist. And that might be really nice for generating assets like 2D avatars and images, as well as maybe 3D models and things like that. And so one quick note, right, let's talk about procedural versus synthetic. Procedural is a deterministic thing, so it's like Perlin noise, right? While it's sort of stochastic in its nature, you're interpolating and it's sort of deterministic once you have that sampling. Synthetic has this sort of stochasticity where it's not entirely random and unpredictable, such as like this StyleGAN from NVIDIA. You can see you can kind of interpolate. It's one of the benefits of StyleGAN. You can kind of go from one style, you can add styles and remove styles and sort of directly interpolate from one to the next. But we don't really know what to expect in the same way that we would with procedural, and that with procedural we kind of know directly what we get. Whereas with synthetic, it's often a sort of implicit representation that we then can manipulate in ways that we don't exactly know how it will change it. Whereas with Perlin noise, I can have a bunch of random points and then choose this one and make it lower, where it's not clear how you're going to do that with an implicit representation, and also not necessarily clear how you would do that with a probability distribution of very, very high dimensional data. So it's a very kind of important distinction to make between procedural and synthetic. So some examples of asset generation approaches is GANs, right? You can literally do this with 2D. Today, as you can see with GAUGAN below, you make a crude image and it will convert it by way of style transfer techniques to what looks like a landscape. You can use autoregressive models, which are very effective. I haven't shown. I showed some examples of them. Actually, didn't talk to this, but as you can see here in the autoregressive examples with Pixel CNN, these images to the right kind of look like images that you would imagine of that size. You can even do this with video. For example, below, these are autoregressive approaches, and you can actually see how interaction with objects can be interpolated and autoregress forward in time. So this is a very cool result. So one obvious utilization of AI, machine learning, is better AI. This is often talked about in the form of reinforcement learning. Many of you may have heard about the AlphaGo, AlphaGo AI agent beating Lee Sedol. And that was a very kind of exciting, but also very sort of solemn moment in a way. This sort of represents what you could do with this stuff. For example, adding more variety in your non-player characters, so your AI maybe can do deeper, more interesting things. You can maybe use this for applications in testing and QA of your game. So maybe it's not part of your game or of your simulation, but this is a way to test stuff, smoke test to try to break it and find bugs. In the case of AlphaGo, I think the most exciting aspect is this sort of like understanding of games in a deeper way, where we saw AlphaGo do certain things that were unpredictable or even creative by some accounts, and trying to understand games in a deeper way using AI, which can play games much faster than we can, might be very interesting, especially with incomplete games and games with massive state spaces that are very difficult to play to completion by a human player. And then finally, this was brought up by Kaspersky. I don't know, the guy who got beat by Deep Blue, the chess guy. I forget his name always, but this is an interesting thing where human beings are very good at executive function, executive decision making, and sort of synthesis of very, very complex, high-dimensional data, whereas machine learning is still not quite good at that, and induction and reasoning. And so if you can combine an AI agent with a human agent to like the AI sort of, it's almost like Star Trek, where you say, what's the simulation of doing this and that, give me the odds and that kind of thing, and then the human agent actually makes a decision. And so yeah, we should also kind of quickly call out the machine learning, the ML agents framework out of Unity. It's one of the more popular ML reinforcement learning frameworks out there. And like I mentioned in this course, you're free to use Epoch, which is the framework that I'm hacking on, and I hope you do. But if you'd like to use Unity for this, they have the ML agents framework for that, or you can do it or use whatever you want. Honestly, it's up to you. But if you do use ML agents, I'm technically in that organization at Unity, so I might be able to help connect the dots as well. Whoops, cool. This is kind of where I'm very interested personally. One of the really unique use cases of ML that's been kind of coming up recently is this sort of implicit representation of geometry. So we talked a lot about this unsupervised learning. You have both implicit and explicit. So this has also been done on the explicit side or the implicit side, but you can use deep machine learning techniques to sort of learn and understand the underlying representation of a geometric data. And people are starting to do this to use machine learning for rendering and things with geometry. So for example, on the top right is Platonic GAN, which from a set of oriented images will extract a volumetric or a voxel representation of the data. One other example is the neural radiance fields, which also, again, given a number of oriented images, will then give you a volumetric implicit representation of your image. It's very, very effective. I recommend all of you kind of check that out. This is something that we'll talk a lot about in the course. And very interesting to me, too, is this sort of deferred neural rendering approach where, say you have a rendering engine, you have all this data, like a deferred rendering pipeline, right? You have your UVs, you have your XYZ, you have your normals, and so on, and you can use that to train a machine learning model against your intended ground truth. So say I have this, even in a graphics engine, I have the RGB, and I also then have these different channels. And if I can train that interaction, that transfer between the different channels to the ground truth, I can then train this neural texture, which is the case in this sort of deferred neural rendering paper, which is very interesting, and then actually manipulate these scenes by way of my neural network without actually having to render it directly. So it's a very, well, it's not directly, I am rendering it by way of these learned rendering functions. And so your rendering is being done using both a neural rendering representation, like a neural texture representation, as well as a neural rendering front-end representation, which is, by the way, also how Platonic GAN is generating these images. There is no graphics engine in there that generates that image, but rather a representation that's trying to minimize the difference between the image that you're seeing and the ground truth, which is in the form of these oriented images. Another very interesting application of machine learning in games is in animation and IK. So if you've done any IK before, you know that IK is a gradient descent process where you're trying to minimize, the error, this sort of error by way of like cyclic gradient descent and what have you. So what ML can do is it can kind of help us in filling in these like in-between frames. So say you have a number of keyframes, and then you want to go from here to here, right? You can interpolate that linearly, but you may get very strange behavior. So, a lot of times, human artists will sit there and fix these things and fill these things in. Or say you have motion capture data from a motion capture system, and you want the animation is from here to here, but you want to change it from here to here, and all of a sudden you do that, and certain things don't look natural, and so a human being has to go again and fix those into between frames. But in theory, if you do that with a machine learning algorithm to kind of train it to change those behaviors, all of a sudden you can output a direct, a machine learning algorithm that when you change a particular parameter, everything else kind of lines up. I don't have much experience with that personally, but the thing that I'm very excited about is motion planning. And motion matching. And motion matching is a very kind of simple idea when you think about it. And what it does is it replaces a particular character animation with a ragdoll, with a physically based ragdoll. And so you have the animation, which is a traditional animation. You can kind of have it walk around. And the ragdoll is trying to emulate, to minimize the loss between its position and the position of that ragdoll at any given time. And so the result is two ragdolls that look or two characters that look about the same, but one is physically based. One is literally stepping on the ground. That, if you poke him, it'll move over. If you throw a rock at them, they'll not get knocked over and try to get back up again. And it's very, very cool. You can actually do this to, just generalize animation and have, characters interact with your physical environment in a much more natural way. So, like, for example, if you've played a game where you have a character and it hits a boundary and it just kind of boop, this would actually, your character would go and kind of trip and kind of respond a little bit to the environment that it's in. Ubisoft has been doing a lot of research on this, and I recommend, and we'll talk about this later if it's interesting, to that. So to kind of finish the lecture, which has already been quite a long one, so I think we're getting to 2 hours no matter what I do here. I've been trying to breeze through this. There's a lot of limitations in machine learning. You might say, wow, this is great. I want to do this right now. But keep in mind, a lot of these models require a lot of computation to train. For example, the Dota 2 bot, the AI out of OpenAI, required around $10 to $20 million to train. So it's just costly in terms of just the computational cost of running these machines or having access to them. The AlphaGo AI required around 2,000 CPUs and around 250 GPUs to run. So it's both expensive from just a computational access, but even just a power consumption standpoint, it's not a cheap thing to do. And AlphaGo largely used a Monte Carlo reinforcement learning approach. So it was like searching through a lot of data to kind of figure out what the best next move would be. So that's great. In these scenarios, we don't really care too much about time and money. Okay, that's fine. So let's move on. Like, what about situations where we do care about time? Keep in mind, games and simulation, they're running in real time, right? So we only have about 16 milliseconds, and we still have to fit in rendering and physics and all that stuff in there too. So, for example, the neural radiance field paper, that really cool thing which can take a bunch of images and turn it into a, implicit volumetric representation, each one of those frames requires about 30 seconds to render. Now, there's improvements being made on this stuff all the time. Like, for example, an improvement to this was neural sparse voxel fields that took down that rendering time from 30 seconds a frame to 1.5 seconds a frame. But that's still not quite real time. And so you have to really think about your utilization of these techniques in the context of a real-time engine or a real-time application. And honestly, real-time ML is not something that a lot of people are thinking about. Although we'll often utilize offloaded or cloud-based things and system design to kind of compensate for, but this is something you really have to think about. Also, memory consumption is a big consideration as well. Remember, in the first part of this lecture, we talked about GPT-3, which is a language model that can generate very, very very what's the word? Very real sounding text. It's a very good text generator. It's very compelling. And the GPT-3 model uses about 175 billion parameters, which is about equivalent to 650 gigabytes of data. And to run that model, you essentially have to run that 650 gigabytes of parameters against your input kind of conditioning data. So this is just a back of the envelope approximation, but 650 gigabytes is a lot of memory, right? It's a lot more than I have on my GPU or on my machine even. And so to run these machines, to run these algorithms, you really start to have to think about memory consumption and considerations of that sort as well. Although there's a whole kind of field of study right now with regards to compression of machine learning models and reducing the number of parameters. And if you're interested in that, let me know. I'm happy to talk about SqueezeNet, for example, and also distillation networks and things like that, which we may discuss in this lecture, in this course as well. There's a lot of really cool stuff going on in that field. So next time, we're going to start to talk about real machine learning models like linear and logistic regression. Linear and logistic regression, I already mentioned the linear a little bit in this lecture. They actually kind of quantify the entire machine learning problem. You have to come up with a model, you have to train that model, so minimize the error of that model to some degree. You have to validate and test that model to see how well you're doing. And then once you have that, you can run that model to infer or to predict new values of data that you have not seen yet before. And so, yeah, next time we'll start to talk about linear logistic regression really quickly and refresh before we get into some of the machine learning stuff, models that we're going to build. And so, yeah, that's about it for this lecture. Thank you. This one was a long one, and hope you all enjoyed it. Bye-bye.